Yeah? Sure. Okay, I'm Frits, but
Hey Frits.
Kids be easy part. We're talking electromagnetic compatibility, and which is about interference. And for interference, you need a source which makes noise and a victim which is susceptible to it, and then obviously the coupling path. And this makes it easy. The coupling path is always wise. But for instance, anything simple, just a piece of copper. Even in the case you have a radio interference, and still you need some sort of wire, antenna, whatever, to get the noise into the air, and then on the other side obviously something to pick it out, which is usually also a interconnection. For a radio it's a real antenna, but if it's a machine it could be a wire loop, cable, whatever you have. So it's always electric interconnections, which makes EMC very easy, which I shouldn't tell next week, but for you it's simple, it's always wired. So I can demonstrate. This is my victim. This is my source. Tune it. But also for you, it's a 32 megahertz oscillator inside, and then we're looking at the third harmonic, which is 96, which is in the middle of a FM band. So this wire is a twisted pair, like twin wires for simple light applications. Usually you see it in a home, which is obviously not suitable to transport this signal. That's actually what you can say. If you get interference, it's not a good cable, right? There's nothing wrong with the box. Then we have this. This is a coax. And then many years ago I did this for machine builders. And then at the end of the show, after 1.5 hours or so, somebody said, oh, it's 2 wires. Yes. So you should know it's 2 wires, so I will tell the guys next week, because that's the same type of guy, that this is 2 wires. An internal wire with a tube around it. But okay, obviously it's much better than this wire. And then we have the same coax wire with a little modification here. And now it looks like this one. The modification is about 3 millimeters of shield removed here, and then a little wire around it. That's all. Which makes a good cable into a leaky one. And that's obviously something we have to watch when you do connectors and that kind of stuff. Okay. This is the setup, because you only have a picture of it. Okay. EMC is defined as follows: the ability of the system to operate according to its specifications, to work in its intended electromagnetic environment. That's what immunity is about. That's one half of the EMC story, and then obviously here we have a picture working, so that's okay. Now we'll see if there's sound. No sound yet. No. The sound on. Okay. Okay, so an airplane struck by lightning. So what would you expect of a system like that when it's struck by lightning? Obviously it should just fly on, right? It did, so it's okay. But we get to that later, that aspect. And there's another one that should also have noise. Let me see, a little louder. Sound is should be on. For some reason we have no sound. Okay, so this is somebody talking on the radio, but there's a lot of noise actually to disturb it. So this is an emission, or yeah, actually when you hear it on the radio, it's an emission problem. There is some equipment that's making too much noise, and the other one, the plane keeping to fly, it's immunity problem. Okay, so without generating unacceptable electromagnetic disturbances in the environment. This is emission, this is immunity. That's the two parts of the definition of EMC, okay? And then there's wavelength. The system could be very large or very small. The effects are identical, unless, see here you have little traces here, so that's interconnection. But this is like maybe 7 centimeters. This could be 100 meters or so. So here you will see effects at a much lower frequency than here. To couple to some device, you need about quarter wavelength, half wavelength would be good frequency to couple to. For people, you would say, well, maybe 30 megahertz, 50 megahertz. For ships, well, 100 meters this time probably would be in the 100 kilohertz. You would have the same kind of problems you would have here for 2 gigahertz or so. So wavelength is important. If it's very small, it's more difficult to couple to low frequencies. If you have a big system, low frequencies could play a role. So it depends on the length of actually your wires. The wires that produce the noise and the wires that pick it up. Okay? The 3 criteria: no internal emissions, which is worldwide. Then we have operate satisfactorily in the EM environment, which is actually something that was added in Europe for the EMC directive. That, yeah, I think they want to protect the customers. That you can't buy stuff that doesn't work in your kitchen or in your home or factory, wherever you're working. So it should operate. I think the Americans only have this. The FCC requires you to be quiet, but for immunity, the cellular market will solve that. That's the American approach. Trumpy, I think, but okay. This is in Europe, so you should also check that it will work in the environment it's intended for. Okay, and then most important, I think, to start with, the system should work at all. I took this from the internet. It's actually a device to catch mice, but you saw it didn't work. Right? This is where you start, usually. But in an EMC lab, you wouldn't notice. You only get these things because this is done at home. people are building stuff, and as long as it doesn't work, they don't come. At some point it does work, then they come and test this. Okay? The bottom part would be self-compatibility. That's what it calls. Okay, I made a list on the insistent request of people from the field, and it's actually required by people, mechanical people with some electronics in their equipment. So the people I was training with this kind of presentation a long time ago, they asked me, can you make simple rules? So of course you cannot make simple rules because it's more complicated than that, but okay, I'll try. So, first 5, all currents run in loops, which means that each signal has a return path. You have to find it and make the loop small. Simple. Every interconnection has transfer impedance. That means every cable, combination of signal and return, will leak to some extent, more or less. And then, if they leak, it will create currents in bigger loops in the area, which we call common mode currents. They also run in loops. It's simple because the current doesn't know that it's common mode. If it would know there's common mode, there's no difference. So all currents are behaving the same. So common mode currents also run in loops, find their return path, and make the loop small. Same story here. Then, this is what you can do against it. This is actually the mechanism, so we can see this is what you can do. Protect interconnections against unacceptable common mode currents. There will be common mode currents, so you can make sure that they don't bother anybody. Okay, and then the most difficult usually, build systems using electromagnetically loosely coupled coherent modules. That's probably not too fit for the audience I'll have next week, but okay, I'll explain. So what you need to do is, you have a very big complex system, try to make as small modules as you can and make them independent. You do that for software, such that you can plug in and out a new module if you need to, without modifying the rest. That's system engineering, and has to do with abstraction, hierarchy, that stuff. And electromagnetically, you don't want that the modules in your system, your hardware platform, let's say, that will create interference, whatever way. And you do that by looking at these two. You look at interconnections and acceptable currents, that would be current boundaries, we'll get to that later. And this is how to apply them, how to put your modules. Imagine you have a printed circuit board, you have 12 ICs, you have to place where do you put them. I think the placement is even more important than the wiring. I mean, if the placement is wrong, it's very difficult to get the wiring right, or this common mode story right, than if you look at it beforehand. So maybe you should look at those. But okay, this is the most difficult part. Then, next step, this is all self-compatibility. If you don't do this, the machine will not work. Afterwards, you have to look that that will work in its environment. Now, I've worked at Thales or Frankis, I think now. They're building Navy ships, and they have a very nasty electromagnetic environment. Very high levels. The enemy doesn't care. You see, so yeah, this is important there. Then you can put the equipment where you want. If it's a home, you have to take care of levels about 3 volts per meter. If it's the industry, you may have to go to 10. Usually in industry you can make a little more noise, but you have to be more resistant against noise, immune for noise. In homes levels to be lower, which is cheaper, and that's actually the reason why they do it. And then, well, you do this, specify the EM behavior of all modules. It's also difficult, because if you get a machine in a lab and they bring it and say, okay, what's the requirements? There's no requirements in the specification. We don't know. So, okay, well, probably it's industry, okay, then we'll take the generic industry levels. If you have special requirements, or you have a special environment, maybe on a platform on sea or something, special environment where you have different environment than in normal industry, it's better to specify it and test it, of course. This is this one. Test it in the environment. Educate employees for EMC environments and awareness, which is important in an industry that is building this kind of stuff, because if you don't do it, then somebody with EMC knowledge will have to go over all equipment and all systems, and if it's a large company, it's very difficult. So at Thales they say, okay, we have maybe 5 or 6 experts that really know, and then we have hundreds of engineers, and if there's something wrong, they will detect it and then call us. That's the way they do it. So the awareness should be there. And then provide support. And if somebody has a problem, you can help. Okay, so this part, the top 5, 6, is what we'll do today. This part is, yeah, managerial system, but it's important, but okay. So the top 6 we will do today.